Okay, welcome back. Any questions? Okay, when we were discussing, but in the last lecture, we stopped here. We were discussing biasing of the transistor while being able to apply the input. We discussed the output side. We were in the middle of discussing the input side biasing. So this is where we stopped. Right, and we were discussing what will be the voltage here, and we agreed that this is essentially we can apply superposition and to find out what will be the total voltage there. And the conclusion that we had was in the absence of this RS, in the absence of this contraption, this would have been fine because we are not drawing any current through VGQ, correct? We are not drawing any current through VGQ because the input current to the MOSFET is 0. So if I apply VGQ here, this voltage will be VGQ. No issues. However, if I now connect these two, then the quiescent current will flow and this VGQ voltage, the gate voltage will drop below VGQ. And one of the suggestions was to raise the value of VGQ. Right? Do you remember that? Yeah. So one of the suggestions was to raise the value of this voltage so that this voltage increases, and also to ensure that whatever, let's say this is, I don't remember what I called it in the previous lecture, but it's called this R1. If R1 was also raised sufficiently, then the entire incremental VI would have appeared across the VGS of the transistor, because from the perspective of VI, R1 is loading. From the perspective of VGQ, RS is loading. Right? So if you don't want loading from the perspective of VI, then you would want R1 to be very high. But if you want R1 to be very high, naturally, the problem is RS is loading VGQ. RS is loading this contraption. So that you cannot honor both. So we were trying to get rid of this problem by increasing the value of VGQ. Right? Let it load, but even after loading, the gate voltage should be sufficiently high. But then we said that this even though this works theoretically, the practical problem is you cannot have multiple voltage supplies to bias your transistors. You generally will have one VDD, and you have to derive all the references, all the other voltages from that power supply. So which essentially means that we are back to square one, because then we'll have to figure out a way to find out this value of VGQ first. So let's assume that the voltage here is supposed to be lesser than VDD. Right? That's a fair enough assumption to make, because if that voltage were higher than VDD, then what problem would you have had? Okay, let me rephrase the question. What I'm saying is that the assumption that I'm making is this voltage, the VGS, required VGS is definitely lower than VDD. Right. So if VGS had to be higher than VDD, then I mean our linear region transistor probably wouldn't have been biased in linear region, right? Because ultimately you have to honor the fact that the drain is at least not below one threshold voltage below the gate, right? Otherwise, it would have been a problem. So it's a fair enough assumption to make that the VGS of the transistor, I mean, the gate voltage of the transistor is not connected to VDD. Again, I mean, the reason I am saying, I mean, there are several other assumptions that goes into the statement that VDD is high, VDD is not very low, the current is, I mean, so on and so forth. If I give you numbers, you'll be able to figure that out readily. But anyhow, that's not the moot point here. The moot point here is that we'll have to derive the voltage of we'll have to derive the voltage at the gate junction from a higher power supply, that is generally VDD. Okay, so the highest power supply in the chip. So you will have to use that to bias all the transistors. If you have 100 transistors, you have 100 amplifiers or 10 amplifiers, everything has to be derived from that particular power supply. Okay, so let's assume that for certain power supply, you require 2 volts. And let's say VDD equal to 10 volt for the time being. Okay, so how do you derive? And your VGQ is not there, obviously, because had it been there, problem would have been solved. So we want to derive 2 volts from 10 volts. What is the best way to do it? Or easiest way to do it? Voltage divider, right? So voltage divider from VDD, great. So let's put a voltage divider. Can you choose values for me? Let's call this R1, R2. Can you choose some values? Pardon? 2 and 8. Okay. So let's say 2 kilo ohm, 8 kilo ohm. Why kilo? Why not 2 ohms, 8 ohms, or 820 kilo ohms, 80 kilo? Current from? Okay, current from the supply. So what is the current from the supply? Now?
1 milliamp.
Yeah, 10 volts by 10 kilo is 1 milliamp, right? So again, we are making an assumption that 1 milliamp is probably not large enough, right? If I say that 1 milliamp is too large, I want 100 microamps, not more than 100 microamps bias current in this stack of R1, R2, then naturally you would have had to increase both R1 and R2 by 10x, right? So that would have reduced the bias current, okay, without changing the ratio. Fine. So let's assume 2K, 8K for the time being. So you have 2 volts there. So now what? Now, how do I connect the input? Should I connect it directly? Let's say RS, let's take value. Let's say RS is also 1K. And this you cannot change. This comes with the previous stage, right? So it's a spec, it cannot be changed, not in your control. So now, if I connect directly, what will happen? Will it work, not work, partially work? Can you speak up? I cannot hear you. You're saying something, right? Okay, so what's the problem with this? Why do I need a capacitor? Pardon? Loading, yeah, right. So essentially, if I connect this, then naturally some current, the current that is in this configuration, obviously if I check it from this side, right, the resistance looking down is what? Is 2 kilo ohm parallel 1 kilo ohm, right? It's no longer 2 kilo ohm. Other way of saying the same thing is this 1 kilo ohm is loading your resistor divider, right? So if this is my box inside the looking inside, so what I'm saying is this part is loading 1 kilo ohm is loading the resistor divider, right? Since 1 kilo ohm is loading the resistor divider, you will have a problem. What is, let's say 1 kilo ohm where in your control, right? Let's assume 1 kilo ohm were in your control, and I can, to prevent loading, I decide to increase the value of 1 kilo ohm to 100 kilo ohm. Then do you think loading will be a problem, or it's okay? It will not be a problem, right? So this becomes 100 kilo ohm. So our DC quiescent point here will almost be equal to 2 volt, because the amount of current that you are drawing through this 100 kilo ohm, I mean, this is essentially 100 kilo ohm parallel 2 kilo ohm is almost 2 kilo ohm. So that's the crux of it. However, what problem will you have? Right. So essentially, you want the incremental voltage at this node to be also equal to VI. Correct? You would want the incremental voltage at this node to be also equal to VI. However, now the parallel combination of, the combination of this, right? What is the Thevenin resistance looking in? R1 parallel R2, right? Thevenin resistance looking in is R1 parallel R2, because to find out Thevenin resistance, you essentially short VDD, right? So both sides of R1 and R2 go to ground. So it becomes 2K parallel 8K, approximately 2K. So R1 parallel R2, which is 2K, is loading RS. So you'll have almost, I mean, a very small value, a very small fraction of VI will appear at the VGS. So again, this will be a problem. So we will have to do something. One of you said capacitor. Yes, capacitor is a solution, obviously. But I mean, if I have to build from scratch, what is the root cause? The root cause is the fact that the DC quiescent, before I connect these two, the DC voltages on this node is what? What is the DC voltage at this node? VI is not DC. VI is the incremental input. No. This node, 0, right? The DC voltage here is 0. What is the DC voltage here? 2 volt. So naturally, if I connect them directly, current will flow and it will load. Correct? So if I have to equalize this voltage to begin with, the best thing to do is probably, if I have access to a battery, I put a battery of 2 volt. So now this becomes 2 volt, this becomes 2 volt. If I connect these two, no loading. Okay. So now again, but the problem is you don't have a battery, but now we know, right? Instead of a battery, we can put a very large capacitor, right? So we'll put a large capacitor, which mimics a battery. So let's call this C1, let's call this C2. So, so naturally, if I put a capacitor at DC, a capacitor is open circuit, nothing loads. So this value becomes 2 volt. This is RS. Let's say RS is 1 kilo ohm. So incrementally, what will this look like? This contraption, this will look like VI, RS, capacitor. And what happens here? I have R2 to ground. What happens to R1? I am replacing the entire stuff with its incremental equivalent. So what? Yeah, so parallel to, so essentially this goes here. If I have to draw accordingly, sorry, this is R1. Because VDD went to ground, this becomes a VG. The transistor gets replaced by its incremental equivalent, which is Y21 times VG. VGS, but source is grounded, so I can get away with VG. So this becomes RT. This is C2. Okay, so on the output side, we have already dealt with it in the last class, right? We had to size the capacitor C2 in such a way that it appeared short-circuited at the signal frequencies, assuming the input is a sinusoid, right? It's a zero mean signal. VI had to be a zero mean signal, otherwise none of it would have made sense. So this is at omega naught. Okay, so what about the now input side capacitor? How do I size the input side capacitor? Pardon? High value. Now, yeah. So ideally, C1 has to be infinite, right? But when you have to design a practical circuit, you cannot put an infinite value capacitor. You put a finite value. So what is the constraint on the capacitor? How do I figure it out? Pardon? Why microfarad? What is so holy about microfarad? Why not nano? Why not farad? Why not pico? So yeah, so instead of giving me the number, can you tell me the thought process? How do I decide? Correct, right? So VG should be very close to VI. That definitely is the case. But to ensure VG is very close to VI, I'll have to also do something with R1, R2. right? So we are now talking about only the capacitor value C1. And we'll get to R1, R2 later. So we are only talking about the capacitor value of C1. So if you don't know anything, what am I trying to ensure? I am trying to ensure that no drop appears across the capacitor. Right? The capacitor should act as a short circuit, right? So given that we know how to deal with these things from previous lecture, can you tell me what is the, I want to look at the circuit and figure out what it is. What is the best thing that I can do? I can find out the time constant associated with that loop, right? So what is the time constant associated with the input loop? So tau 1, let's say, is basically Rs plus R1 parallel R2 times C1. This has to be much greater than or much less than 1 over omega naught, which means C1 has to be right. So now when you do calculation, it's picofarad, microfarad, nanofarad. It depends on the values you choose. There's nothing holy about microfarad. Okay, so so this is as far as to ensure that C1 acts as a short circuit. Now, let's assume C1 acts as a short circuit, right? So we're approaching the design one step at a time. If C1 acts as a short circuit, then in order to ensure VG is approximately equal to VI, as you pointed out, what do I need to ensure? So only ensuring C1 is short circuited, is it fine, or do I have to ensure something else also? Right. So R1 parallel R2 should not load the input side, right? So capacitor anyway doesn't come into picture anymore because we have sized the capacitor so that it's a short. Okay. So essentially, if I have to sketch the input side, this becomes VI RS, capacitor is a short, and I have R1 parallel R2. This is VG. Correct? And we expect VG to be almost equal to VI in a good design. Right? If VG is almost equal to VI, then what do we need to ensure? I need to ensure R1 parallel R2 is much greater than RS. So essentially, this guy does not load RS. Right? So that's all we need to ensure. So if you ensure these, your design, I mean, you kind of know what values to choose, right? So any questions? Okay. So let me ask you one follow-up question on this. So let's say the MOSFET that you have has some input current, some leakage current or something, right? So let's say it has some IG. Let's say it's a constant IG. Let's say IG is, I don't know, 1 microamps, right? Or let me increase it further. Let's say IG is 10 microamps. This is absolutely large number for IG, but for the purpose of this discussion, let me take that value. So do you think anything changes? Why? Why not? Or why? No, that's what I'm saying. Let's say there is a the oxide is not a very good oxide, right? So there is a leakage current into the gate. Let's say this is a fact. I'm giving you an additional constraint. So do you think anything will change in your design process? Or, I mean, tell me what might get affected. Do you think this IG will load these guys, the input? IG is a bias current. I mean, bias a DC current. Correct, right? So essentially, current. So what he is pointing out is, so firstly, let's take one step at a time. So since the capacitor is open circuited for DC, so this guy is not a problem, right? So I don't have to worry about the input. But what about the bias? So as he is rightly pointing out, so if there is a current that is going into it, so then clearly the current that is going into, clearly the current that is going through R2 has reduced, right? In fact, the current in the entire stack would have changed, correct? So essentially what would have happened, this voltage would move from 2 volt. It will go up or go down? It will go down, right? So naturally it will go down. How much will it go down by? Yeah, exactly. No, it will not go down by Ig into R2. So let me sketch the circuit separately. So let's say this is VDD. What I'm saying is this: you have a current source here, Ig, and this is the voltage source, VDD. What is this voltage? You superposition, right? So this is, in the absence of Ig, this is VDD times R2 by R1 plus R2. In the presence of Ig, to short VDD, this becomes minus Ig times R1 parallel. Correct? So this is the effect of loading. So what do you need to ensure in the presence of Ig? Let's say Ig is a fact of life, it will be there. Then what do you need to ensure? How does your design decisions change to ensure that the transistor is still biased properly? Pardon? Right. So in essence, I have to ensure that this turn is much less than this turn. Correct? So I have to ensure that the additional drop that is happening because of this Ig is much lesser than the original voltage that I would have had. So essentially, you'll have to ensure that this guy is much greater than that guy. Then you choose your R values, right? So you get an additional constraint. Okay. Any questions? Yes.
From here, from this constraint, we'll get the R2 plus we'll get only one constraint on R2.
Correct. You will get one constraint on R2. Yes.
There's not getting any constraint on R1.
No, you essentially have two constraints to choose, right? You have one constraint here, and you get another constraint here, right? So then you can have, I mean, if you only deal with this constraint, you only have the ratio information. You don't have the absolute information. So you need another constraint that might come from here. I'm not saying it will always, sometimes it doesn't. I mean, and sometimes it will. Okay, again, I mean, the motivation of this entire course is to make you think, right? So give you situations which might not always be straightforward or something that you have to think on your own, right? So that's my job here. So make you think. Okay. Yes. I didn't understand. Can you repeat your argument? Right. Okay, tell me what you have to do. You know Ig, right? So what do you get? So it essentially Ig times R1 by R1 R2 by R1 plus R2 is much less than this goes. So you choose R1 such that this is much less than what? By Ig. Right? So algebra is the easy part, right? So yeah. So once you put the constant together, you can do the algebra, right? So, but putting the constant together is the part of the designer, the job of the designer, rather. Okay. Any other questions before I move forward? No? Okay. So till now we have been dealing with the transistor kind of as a black box, and so let's spend few minutes on the current voltage equations of the transistor from the perspective of the device. So the equations that we have been dealing with till now was IDS is beta by 2 VGS minus threshold voltage whole squared, where this is ITS. But we know that from our experiences in device physics that beta is essentially what? Yeah. So this is mu n C ox W over L VGS minus threshold voltage whole squared. Let me sketch the cross section of a MOSFET, and let's define these terms once for the sake of completion. So let's say you have a p-type substrate, and you put a oxide on top of it. So this is the dielectric, an oxide, and then you put a thin layer of metal. This is on top of it. Then on either side of this contraption, you dope it with some highly doped N plus. Plus means highly doped. From a highly doped N plus dopants, right? So, and you put contacts out. So for all practical purposes, this guy acts as a metal. This guy acts as a metal. I mean, as a conductor, not a metal. And now you have to decide. So this is physically symmetric, right? You cannot really make out which is what. This is essentially the gate. Now, let's say I call this one drain, I call this one source. But how do I make the distinction between what is drain, what is source? Body I can connect to anything, right? Let's say body is here, I connect it to ground. So how does it help me in identifying which is drain, which is source? Biasing what? Right. So one that is at a higher voltage is a drain, correct? So electrically there is a distinction. Geometrically there is no distinction. If I decide to apply higher voltage this side, this will be the drain. Okay. So now let's assume we have so let's say this is body. Let's ignore body for the timing. We'll come to body later on. So let's say we have a voltage, just put the body connection plus, and let's assume this is also grounded. So we need a reference. Let's say this reference is ground. Okay, so now we apply a gate to source voltage, and we also ensure that the drain voltage, the drain to source voltage is also applied, right? So VDS is also applied. And if we assume that VDS is greater than 0 and VGS is greater than the threshold voltage, so if VGS is greater than threshold voltage and VDS is greater than 0, what should I see? I should see electrons under the oxide in the channel, right? So I should see mobile electrons in the oxide under the channel. If I now decide to reduce VGS, what's going to happen? The number of concentration of the electrons in the channel will reduce, right? And if I decide to turn off VGS to below threshold voltage, the electrons in the channel will disappear, right? So essentially, it's like a tap, right? You turn the tap on, you have water. You turn the tap off, water. There is no water flow, right? So the tap essentially is the VGS, but how much water will flow or how much current will flow between drain and source is dependent upon the VDS, right? So the lateral electric field, this guy decides how much of the charge will flow between drain and source. Okay, so this is quite simplistic. Now, as it turns out, if you make VDS just equal to threshold voltage, VGS minus threshold voltage, something interesting happens. What happens? So, okay, so let's assume to start off, so let me maybe spend a couple of minutes on this. Let's increase this size. So let's say VDS is equal to 0 and VGS is greater than threshold voltage, then there is no distinction between source and drain, correct? VDS is 0, VGS is greater than threshold voltage. You cannot distinguish which is drain, which is source, which means whatever profile of the charge you see in towards the source side will be identical around the drain side, correct? So you will have electrons uniformly distributed through the channel. Now, if you increase VDS, now if I keep on increasing VDS, what is happening? I can imagine that this is a in essence I can imagine this is a small MOSFET cut into smaller sections, right? These are all small MOSFETs with individual oxides on top, correct? So I can imagine this. You can imagine that this is a MOSFET, this is a MOSFET, this is a MOSFET, this is a MOSFET. They are all stacked next to each other. Correct? So for each of them, I have small channels. Correct? So if I increase VDS, which means that the channel voltage here, increases than the channel voltage towards the source side. Correct? So what can you comment on the voltage difference between the gate and the channel towards the drain side as compared to the voltage difference between the gate and the channel towards the source side? Which one will be high? The source side, effectively the MOSFET towards the source side will be turned on more, or MOSFET towards the drain side will be turned on more? Source side will be turned on more, correct? So because the source side will be turned on more, so naturally I can argue that the concentration towards the source side of the electrons will be higher than the concentration of the electrons towards the drain side, right? So if I sketch the electron profile, so concentration of the electron profile should look something like this, correct? And if I keep on increasing the drain voltage, this trapezoid will start to become a triangle. And what happens when at this junction, I increase the VDS to such an extent that the VG channel at drain becomes threshold voltage. Conduction doesn't stop, right? So that's what, right? So what happens then? I mean, we'll get to conduction, but what happens then? Essentially, you don't have any inversion charge. You don't have any mobile carriers left. So essentially, you have, this becomes a perfect triangle, almost like a perfect triangle. You don't have any channel charge at the drain channel junction, right? So yes.
The inversion charges actually go to the drain side, right?
Right. Yeah. So that's true. So that's the dynamic phenomenon, right? As you keep on increasing, where does the charge go? But we are not talking about the dynamic phenomenon. We're talking about, you have increased the channel, you waited for some time, you are trying to see what the charge profile is. So now when this happens, and you further increase the VDS, right? When you further increase the VDS, you cannot really influence the channel charge anymore, right? Because there is no charge to influence at the drain channel junction, correct? So this is what we call pinched off or in other words, this is a pinch off phenomena, or in other words, what we say is that the current that was I mean, when we are increasing VDS, the electric field was increasing, and since the electric field was increasing, we were getting higher and higher current charges flowing from source to drain. But now, because this channel charge distribution will not be affected anymore, whatever current I was getting just at the pinch off will be one constant, right? I cannot increase the channel. I cannot increase the current any further, right? So essentially, my current gets saturated. So current gets saturated to some ID sat, and the value of ID sat is right here. Mu n refers to the mobility of the electrons, and naturally, when you are talking about charge flow, these are with which the charge flows should depend upon the mobility of the electron or the conducting body in the material, that is referred to as mu, in this case electrons, so negative charge, so mu n. Cox is, I mean, naturally this is oxide. You have oxide layer, you have a metal on top, you have oxide on bottom, in the middle, and a channel charge which acts as like another metal plate. So essentially you have an oxide between the gate and the channel. So this Cox is the oxide per unit area, right? So this is the oxide per unit area. This is epsilon ox by Tox, not times WL, right? W and L is the length of the channel. L is the length of the channel, and it makes sense. Longer the channel, lower will be your current, because I mean, for per unit time, the amount of, I mean, the proverbial electron will take more time to flow from left to right if the channel is larger. So your current will be lower. What about W? The W is not evident from this diagram. To see the W, you'll have to see the lateral side of it, right? So if I attempt to sketch a 3D version of this, so this should look like. Let me remove these biasing stuffs here. So this is drain. Similarly, you will have a source which is coming somewhere from here, and you have a gate. So if I assume that, okay, before we assume, let's do the definition first. So this lateral dimension is the W, right? So it's basically, I mean, W in the sense of current flow through a tap is essentially the width of the pipe, right? So if you have thicker pipe, you will have more water flow. In this case, if you have higher W, right, you will have more current. Okay. Any questions on this? Again, I am assuming that you are familiar with MOS transistor, at least the basics of device physics of how this works. Okay, so this is as far as a very basic structure of our MOSFET is concerned. But however, there is one interesting thing that you should bear in mind while staring at this saturation current equation. So what are the design variables here for a designer, for a circuit designer? What are the variables that you can play with, and what are the variables that you cannot play with? Can I play with mu n? No, right? So once you decide on the material that you are going to use, your mu is fixed. Can I play with Cox? We can, but then, I mean, moment you say that I'll be using a device that has been given to us, right, by our device colleagues, then you don't have, right? So COX definition is a design parameter if you are designing the device. Now, if you are using the device to make a circuit, then COX is not in your control. You use it, whatever you have. So for a circuit designer, COX is not a variable of choice. You have it, you take it and use it. What about threshold voltage? Kind of fixed. You can, we'll see later on, you can change the threshold voltage slightly in some ways, but for more, I mean, for most practical cases, threshold voltage also doesn't change significantly to cause a lot of impact. VGS clearly is in our control because we are applying the gate voltage, we are applying the source voltages. W and L. This is slightly tricky because when you decide to use a device, you are also deciding the values of using the W and L of the device, right? So when you are, let's say you buy a MOSFET from the market and for your breadboard circuit, right? So W and L are fixed for that. You cannot change them. Correct? However, when you are designing an integrated circuit, the design flow allows you to change W's and L's. So essentially, one time during design, you can decide what will be your W of a transistor, what will be the L of a transistor. But once you fix that, you cannot change it. Right? So it's a one-time offer essentially, right? You can change your, so you can influence the current in your circuit by designing appropriately and sizing W's and L's appropriately, right? But you have to be careful. Once you fix it, you cannot change it. That's not true for gate to source voltages. You can keep on changing it even during testing or in the lab. Okay. So W and L are also design variables, but these are one-time design variables. Okay. So here it looks like I can, if I desire certain current of ITsat, right? For whatever reason, maybe I required some GM, maybe I required some transconductance, I required a value of ITsat. Then if W and L is my design variable, VGS is also my design variable, then it looks like I have infinite possible ways of fixing ITsat. Right? Ultimately, multiplication of these two terms is supposed to be constant. If ITsat is supposed to be constant, right? Or if I desire a certain value of ITsat, then the question begs: is there a better choice, or like all choices are equal, right? So before we go there, one caveat is, okay, before I even talk about the caveat, let's say I decide to test the validity of this model, right? So let's say I say that for a particular value of ITsat, let's say I fix ITsat equal to 1 milliamp, and what I'm trying to see, if I keep on increasing W by L, right? Essentially what I'm saying is, if I keep on making this MOSFET fatter and fatter, right? It becomes fatter than this page. Then what essentially we have to do in this equation to ensure ITsat stays at 1 milliamps? Reduce VGS minus threshold voltage, right? So if I make W by L tends to infinity, then VGS minus threshold voltage tends to 0, right? So as it turns out, there is a validity limit of this model. You cannot stretch it beyond something. You can stretch it approximately till this VGS. This is valid approximately when VGS minus threshold voltage is greater than 3 kT over Q, which is approximately 78 or 80 millivolts. So this is the validity of the model. It's a physics-based model. So again, it's a piecewise linear model, right? This model is not valid in certain regions, not valid, valid in certain other regions. So one of the limitations of this model is that you can use this as is when VGS minus threshold voltage is at least 80 millivolt or higher, right? So 80 millivolt is a weird number. For our course, will settle on 100 millivolt. Let's assume VGS minus threshold voltage is 100 millivolts or higher. Then we are good to go with this model. Okay, so that is something you should keep in mind, that you cannot really, while trying to fix a current, you cannot really go crazy with W by L, because the validity of the model will break down. That is not to say that the current will, the transistor will stop working. Transistor will still work, but you cannot use this equation to come up with any conclusions. Okay. Okay, fine. So So, but again, as it turns out, this equation is also not foolproof, right? So there is a better version of this equation. Now recall that what we said is if we keep on increasing, if we keep on increasing the VDS beyond saturation, the current does not increase anymore, right? So that's what the definition of saturation voltage was. But that statement is also not fully true. It's not fully true because what happens if I zoom in around the drain channel junction, as it turns out, if you increase VDS, this electric field increases regardless. Just that I was interpreting that it's not able to influence the channel charge to the first order, correct? But that is also not particularly true. As it turns out, it's able to push the channel charge slightly to the left, right? So if I increase VDS, as it turns out, this guy pinch off region essentially can move slightly to the left, right? So essentially what happens is the new channel, the electrical length of the channel reduces by a certain amount. So the electrical length of the channel, let's say, reduced by delta L, correct? So clearly delta L is a function of VDS, right? It's I mean, in the absence of anything, I can say that it's a nonlinear function of VDS, right? It's there, right? However, we are not device physicists. We try to figure out what is the impact of anything, right? So, right. So the impact of this is the fact that your ID sat equation becomes W by L minus delta L, because essentially the length of the transistor has reduced times VGS minus threshold voltage whole square. So this L minus delta L, right? So if I club these things together and I express this as L within parentheses 1 minus delta L over L, and as it turns out, delta L is a weak function of VDS, right? That is how your transistor is. It was supposed to be 0, but it's not 0. There is a second order effect, and because of that, your delta L is finite. However, delta L is not a significant portion of L. If delta L becomes significant portion of L, your transistor action will get lost, right? So our device colleagues have ensured that they make devices in such a way that delta L is much less than. So if that is the case, I can use Taylor series. So this essentially becomes 1 plus delta L by L. Yeah, W by L, 1 plus delta L over L. Now recall that I said that delta L is a function of VDS, right? And in the absence of anything, I can, if this is a nonlinear function of VDS, what can I say? This essentially is, if I say that I have to evaluate this nonlinearity, what do I need to do? What is the easiest way to deal with nonlinearities? Taylor series, right? So I have to expand this around a quiescent point, right? So what should I expand this around? Around some VDSQ, right? Whatever VDS I had, right? So in this case, VDSQ will be the pinch off point, because this phenomena started occurring at the pinch off, correct? So this has to be at the pinch off. So what was delta L at pinch off? No, delta L. It was 0. So the first term goes to 0, right? So the additional terms will be something proportional to some alpha times VDSQ. Sorry, alpha times delta VDSQ plus higher order terms times delta VDSQ whole square plus blah, 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 blah. Correct? So again, like a Taylor series, we take the first term, we ignore the others. So this becomes ID sat becomes half UN Cox 1 plus some alpha delta VDSQ over L. And this alpha over this guy, alpha over L, is popularly referred to as lambda in the literature. And we call this then this should have been delta, okay, delta VDSQ because we are doing on top of VDSQ. Right? Okay. So in other words, what I'm saying is the current voltage equation or the current voltage plot of IDS with respect to VDS, which was in saturation, which was supposed to be constant, right? It was supposed to be half mu n Cox W over L PGS minus threshold voltage whole square. This is what it was supposed to be, but now it's not that. It has a slope. Okay. And again, another approximation is this delta VDSQ is supposed to be the VDS on top of the pinch off point, right? This is supposed to be delta VDSQ. As you go higher and higher to the right, your delta VDSQ increases, so the effect of this term starts to become more prominent. But again, this becomes sometimes messy to deal with when you are talking about doing quick and fast calculations. So the approximation that we do is very often we say that this delta VDS, this guy, from wherever we started off, right? This additional offset is negligible with respect to the pinch off point. So we say that this delta VDSQ will approximate as VDS. Right, so this becomes your ID side equation essentially is often approximated as okay. So this is the standard equation that you see in the literature, and this is what we'll be using throughout the course. Again, a quick disclaimer. This equation also is not a particularly valid equation for defining a MOSFET. If you are doing device physics, if you are doing transistor modeling courses, you will see that there are like more than 100 parameters that are used to define the current voltage relationship of a MOSFET. But you cannot possibly design any circuit with keeping 100 parameters in your mind, right? So as it turns out, we will use this, and this is a good enough approximation to understand what are the effects of changes in a circuit to a device. I mean, what are the effects? What are essentially the knobs that you need to have to influence the characteristics of a transistor, right? So don't get too much bogged down with the fact that this is square, that is linear, and so on. So what you need to understand to be a good designer is, what do I need to do to increase the current? What do I need to do to decrease the current? How much it will increase by or how much it will decrease by is best left to the numerical simulator, right? Or a calculator, right? But as a designer, you need to know what should I do to increase something or decrease something, right? Just like when you go to turn on your tap, you don't write equations, right? You know that you have a general idea that if I turn it this way, your flow will increase. If I turn it the other way, flow will decrease. You really don't know how much you need to turn it by unless you test it with, right? So you develop an intuition based on the experience of turning the taps on and on. Similarly, here also you will develop an intuition if you engage with the circuits more often than not. For the purpose of problem solving in this course, yes, these equations will be valid. But again, You'll have to understand which are the dominant terms in an equation. For example, let's do a quick example here. So what is the Y21? By the way, Y21 in a transistor is often referred to as GM, or the transconductance. We'll be using GM from now on. So what is Y21? ID delta VGS, which will be, in this case, what? Mu n C of W over L, VGS minus threshold voltage, times 1 plus lambda VDS, right? VDS Q rather. These are all Q, let's say, because evaluated at certain quiescent point. Okay. So now you will often see that this is, okay, so in an ideal transistor where you don't have this lambda term, right? By the way, one more terminology, the effect of reduction of channel due to the application of VDS is called channel length modulation, right? So yeah, so this term appears because of channel length modulation. Or popularly abbreviated as CLM. So in an ideal device, the effect of channel length modulation is negligible, right? It's absent. In a real device, it will be present, but do you think it will be dominant or it will be not that dominant? It will not be, I mean, we can expect it to be not that dominant. And as it turns out, lambda, the value of lambda is often of the order of 0.1 volt inverse or less, right? So essentially the slope you can see is not as much, right? 1 plus lambda VDS will be what, 1 point, I mean, if VDS is, let's say, 1 volt, so the additional term is like 10% higher, right? And so what I'm essentially pointing to you is that even if you neglect this 1 plus lambda VDSQ term, you will not incur too much error in calculation of IDS or even in the calculation of GM, right? So that is why this term is often dropped, and we call this mu n C ox W over L VGSQ minus threshold voltage. Okay. However, if you are trying to calculate Y22 is what? What is the definition of Y22? Delta ID by delta VDS, right? Basically, del I2, del V2 in the two-port parameter. So what will that be in this case? Differentiate the equation with VDS. So we get half mu n C ox times lambda. Now, if you neglect lambda in this case, if you neglect channel length modulation, you will get 0, right? So now you cannot neglect anything with respect to 0, right? You will have infinite percentage error, one might say, right? So as a designer, you'll have to see when you can neglect something and when you cannot, right? So if GDS, or if this is often called also GDS, conductance between drain and source. So if you are planning to neglect GDS, you have to ensure that there is something connected to the circuit which is dominant, I mean, so that it allows you to neglect GDS. If GDS is the only thing that is there, then you cannot neglect. I mean, again, the statement will become clear shortly. But what I'm trying to point out here is that in isolation, you cannot really neglect Y22. Because if you neglect Y22, you are essentially saying that I'm neglecting something with respect to 0. You can neglect something with respect to a non-zero value, depending upon whether this guy is lesser than 1 or near about 1. But here, you cannot neglect lambda because there's nothing to compare with. Okay, so high, low, good, bad, all these things are relative terms. So whenever you are making such a statement, you have to, back of your mind, you have to tell yourself that this is with respect to something. You need to know which is respect to what. right? So in this case, there is nothing to be with respect to, so we cannot neglect. Yes.
By comparison out.
Right. So that's what I meant when I said that you have to see with respect to what. So that depends on the circuit topology. If there is already an R out associated or RL associated, then with respect to that, you might be able to neglect, right? So that we'll see. Okay. So these equations are also, I mean, you will see that these equations are also expressed in multiple ways. So if I can, the crux of the matter is that if I can neglect lambda while calculating GM and while calculating I, then I can say that this is equal to approximately equal to IDS times lambda. So GDS becomes IDS times lambda because this term becomes IDS. So this is one equation, this is one expression that is popularly used. Similarly, in case of GM, right? So in case of GM, we say that this is equal to mu n C of W over L, GSQ minus threshold voltage is Q, right? This can also be expressed as if I essentially replace the value of VGSQ from the current equation, right? So I know that IDSQ is right. So if I basically plug in the value of VGSQ minus threshold voltage from this equation, what should I get? Yeah, right, under root twice mu n C ox W over L times IDSQ, right? So this is another equation of GM which is also very popularly used, and it will come in handy, right? So, but now the question is, are both of them telling you the same thing or they are telling you the different things? They are essentially telling you the same thing, right? But if you are not careful, you might interpret it in different ways at times, because what is this equation telling you? This equation is telling you that GM is proportional to under root W by L, right? So if I increase W by L by 4x, GM will increase by 2x. What is this equation telling you? If I increase W by L by 4x, GM will increase by 4x. So same GM. Right. So your IDS, so so essentially what you have to keep it in mind is IDSQ is dependent on W by L, right? So if you increase W by L, IDSQ is not staying constant, right? So there is a hidden variable inside which will, which essentially will also increase the GM. So again, it depends upon what type of biasing you have used, right? Again, those things will become clear shortly. So what I'm essentially saying is, if let's say I have a current source, right? So till now, what we have seen, we have given a voltage at the between the gate and the source of the transistor. We generated some current, and we did all our calculations based on that. Correct? So let's assume that somehow magically I have fixed the current. Right? How, we have not yet discussed. Let's assume that I have fixed current. Right? Then what I'm essentially saying is that I have put my circuit together in such a way that IDSQ is constant. Then can you comment on, if I increase W by L by a factor of 4, how much will GM increase by? What I'm saying is, assume IDSQ is fixed. We haven't seen how to do that yet, right? So let's assume that somehow magically we have done this. Then after we have done this, then we increase W over L by a factor of 4. How much will GM change by? 2 times. Why not 4 times if I look at this equation? Right. Yeah. So when we say when we say IDSQ is fixed, so this is the mother equation, right? So when you say IDSQ is fixed, what we are essentially saying is, if I increase W by L, what am I doing? I am naturally saying that somehow in my circuit, I am reducing VGS minus threshold voltage. Correct? In order to compensate for the increase, since IDSQ is fixed, if I increase W by L, I have to reduce the VGS minus threshold voltage. Right? So which essentially means that if I look at this equation, then the VGS minus threshold voltage is a function of IDS. Right? The situation has reversed because somehow I have made IDS fixed. Okay. So again, which equation to use depends on the context. Right? So you, based on your observation, based on the context, based on the design, you might choose to use one or the other. Again, both the equations will give you, or all equations should give you the same results, provided you understand the variables that you are using in your equations are dependent, independent, how they are varying, if you change certain variable and so on. Right? So equations are always there to be used, but how to use depends on the user. Okay. Okay, fine. So now what is the what is the model of our MOSFET now? What is the incremental model? The incremental model of our MOSFET changed from this was GM times VGS, this source, this is drain. It changed from being this to having a VDS. Okay. So if this has changed, so how does it affect our original design? So original design was so let's say we know how to bias it and we don't have to bother it as with biasing too much. So this is and we are taking output across V0. Okay. So how does thing change here? So where should I, if I have to go from this transistor model to the incremental model, what should I do? Let's say at the input side, what should I do? De-energize VGQ. That's gone. What about VI? VI would remain. VI should be connected between gate and source. So VI gets connected here. The transistor gets replaced with its incremental equivalent, which is already placed. Where should I put RL? Between drain and one side is drain, other side will be drain and ground. And what is ground in our case? Ground is source, so essentially this is ground. So that's very convenient. So this becomes RL, and since we are dealing with conductance, let me call it GL. So now, what is V0? VGS is VI, right? So the current is GM times VI flowing into a parallel combination of GDS and GL. So this becomes minus GM times VI. What? Okay. So now, if you say, I mean, as he was pointing out, in this configuration, it's probably sometimes possible to neglect the usage of GDS, because if GL is much greater than GDS, right, then V naught will be approximately minus GM times VI over GL, right, or minus GM RL times VI. Correct? So why am I saying this? This is obvious algebraically. The reason I'm saying is if you know a priori how much GDS you typically get, what is the GL that you are trying to drive, then you can ease your calculations by saying that in the transistor model itself, I will not include GDS. Your transistor model gets simplified. And this might not be significant when you are using only one transistor, but if you have like 6, 7 transistors in a network, right? So you can essentially reduce the number of nodes, number of equations significantly by making these approximations, right? So knowing what is the load, how you are planning to drive that load, what is the typical GDS that you can get, can significantly improve your design process. Okay. So again, it's not about calculations, it's about thinking and making the approximations, right? So if you make I keep on saying this, that the difference between a not so good designer and a very good designer is how accurately you make approximations. It's not about calculations, right? We are not, I mean, for calculations, I mean, you have calculators, you have simulators, right? So again, the example that I give, knowing how to learn, knowing how to use a calculator doesn't make you a good mathematician, right? Similarly, knowing how to use a simulator does not necessarily make you a good designer, right? You have to make the approximations right. I mean, just like a calculator, a simulator will give you garbage if your input is also garbage. Okay, fine. Any questions before we wrap up? No? Okay, fine. So we'll stop here.